What is a moduli space? A moduli space is a manifold or variety which parameterizes some class of geometric objects. The G invariant classifying elliptic curves up to isomorphism and the Jacobian variety of an algebraic curve are typical examples. In a broader sense, one could include as another classical example the classifying space of a Lie group. In modern mathematics, the idea of moduli is in a state of continual evolution and has an ever-widening sphere of influence. For example, by defining a suitable height function on the moduli space of principally polarized abelian varieties, it was possible to resolve the Shafarevich conjectures on the finiteness of abelian varieties, Faltings 83. The moduli space of major classes of two-dimensional representations of an absolute Galois group is the spectrum of a Hecke algebra. The application of these results to resolve such number-theoretic questions as Mordel's conjecture and Fermat's last theorem are memorable achievements of recent years. Turning to geometry, via Donaldson invariants, defined as the intersection numbers in the moduli space of instanton connections, one can show that there exist homeomorphic smooth four-manifolds that are not diffeomorphic. Indeed, Donaldson's work became a prototype for subsequent research in this area. Here's an analogy. When natural light passes through a prism, it separates into various colors. In a similar way, one can try to elucidate the hidden properties of an algebraic variety. One can think of the moduli spaces naturally associated to the variety, the Jacobian of a complex curve, the space of instantons on a complex surface, as playing just such a role of Netter's hidden colors. The aim of this book is to explain with the help of some concrete examples the basic ideas of moduli theory as they have developed alongside algebraic geometry. In fact, from long before the modern viewpoint sketched above. In particular, I want to give a succinct introduction to the widely applicable methods for constructing moduli spaces known as geometric invariant theory. If a moduli problem can be expressed in terms of algebraic geometry, then in many cases it can be reduced to the problem of constructing a quotient of suitable algebraic variety by an action of a group such as the general linear group GLM. From the viewpoint of moduli theory, this variety will typically be a Hilbert scheme, parameterizing subschemes of a variety, or a quad scheme, quotient scheme, parameterizing coherent sheaves. From a group theoretic point of view, it may be a finite-dimensional linear representation regarded as an affine variety or a subvariety of such. To decide what the solution to the quotient problem should mean, whoever forces us to rethink some rather basic questions. What is an algebraic variety? What does it mean to take a quotient of a variety? In this sense, the quotient problem, present from the birth and throughout the development of algebraic geometry, is even today sadly lacking an ideal formulation, and as one sees in the above examples, the moduli problem is not determined in itself but depends on the methods and goals of the mathematical area in which it arises. In some cases, elementary considerations are sufficient to address the problem, while in others much more care is required. Maybe one cannot do without a projective variety as quotient, maybe a stack or algebraic space is enough. In this book, we will construct moduli spaces as projective algebraic varieties. B. Algebraic varieties and quotients of algebraic varieties. An algebraic curve is a rather sophisticated geometric object which, viewed on the one hand as a Riemann surface or on the other as an algebraic function field in one variable, combines analysis and algebra. The theory of meromorphic functions and abelian differentials on compact Riemann surfaces, developed by Abel, Riemann, and others in the 19th century, was through the efforts of many later mathematicians deepened and sublimated to an algebraic function theory. The higher dimensional development of this theory has exerted a profound influence on the mathematics of the 20th century. It goes by the general name of the study of algebraic varieties. The data of an algebraic variety incorporates in a natural way that of real differentiable manifolds, of complex manifolds, or again of an algebraic function field in several variables. A field K is is called an algebraic function field in n variables over base field k if it is a finitely generated extension of k of transcendence degree n. And indeed, any algebraic variety may be defined as by patching together the spectra of some finitely generated subrings R1 to Rn of a function field k. This will be explained in chapter 3. This ring-theoretic approach from the viewpoint of varieties as given by systems of algebraic equations is very natural. However, the moduli problem, that is, the problem of constructing quotients of varied varieties by group actions, becomes rather hard. When an algebraic group G acts on a affine variety, how does one construct a quotient variety? An algebraic group is an algebraic variety with a group structure, just as a Lie group is a smooth manifold which has a compatible group structure. It turns out that the usual quotient topology and the differentiable structure on the quotient space of a Lie group by a Lie subgroup fail to work well in this setting. Clearly, they are not sufficient if they fail to capture the function field together with its appropriate class of subrings of the desired quotient variety. The correct candidates for these are surprisingly simple, namely the subfield of G invariants in the original function field K and the subrings of G invariants in the integral domains are an element of K, see chapter 5. However, in proceeding one is hindering by the following questions. 1. Is the subring of invariants Rg of a finitely generated ring R again finitely generated? 2. Is the subfield of invariants Kg belonging to K equal to the field of fractions of Rg? 3. Is Kg belonging to K even an algebraic function field, that is Kg finitely generated over the base field K? 4. Even if the previous questions can be answered positively and an algebraic variety constructed accordingly, does it follow that the points of this variety can be identified with the g-orbits of the original space? In fact, one can prove property 3 quite easily. The others, however, are not true in general. We shall see in section 2.5 that there exists counterexamples to 1, even in the case of an algebraic group acting linearly on a polynomial ring. Question 2 will be discussed in chapter 6. So how should one approach this subject? Our aim in this book is to give a concrete construction of some basic moduli spaces as quotients of group actions, and in fact we will restrict ourselves exclusively to the general linear group GLM. For this case, property 1 does indeed hold chapter 4 and also property 4 if we modify the question slightly. See the introduction to chapter 5. A correspondence between g-orbits and points of the quotient is achieved provided we restrict in the original variety to the open set of stable points for the group action. Both of these facts depend on the representation theoretic property of GLM called linear reductivity. After paving the way in chapter 5 with the introduction of affine quotient varieties, we globalize the construction in chapter 6. Conceptually, this may be less transparent than the affine construction, but essentially it just replaces the affine spectrum of an invariant ring with the projective spectrum pro of a semi-invariant ring. This global quotient, which is a projective variety, we refer to as the pro quotient rather than projective quotient in order to distinguish it from the other constructions of the projective quotient variety that exists in the literature. An excellent example of a pro-quotient and indeed of a moduli space is the Grassmannian. In fact, the Grassmannian is seldom considered in the context of moduli theory, and we discuss it here in chapter 8. This variety is usually built by gluing together affine spaces, but here we construct it globally as the projective spectrum of a semi-invariant ring, and observe that this is equivalent to the usual construction. For the Grassmannian G2n, we compute the Hilbert series of a homogeneous coordinate ring. We use this to show that it is generated by the Plucker coordinates, and that the relations among these are generated by the Plucker relations. In general, for a given moduli problem, one can only give a honest construction of a moduli space if one is able to determine explicitly the stable points of the group action. This requirement of the theory is met in Chapter 7 with the numerical criterion for stability and semi-stability of Hilbert and Mumford, which we apply to some geometrical examples from Chapter 5. Later in the book, we construct moduli spaces for line bundles and vector bundles on an algebraic curve, which requires the notion of stability of a vector bundle. Historically, this was discovered by Mumford as an application of the numerical criterion, but in this book we do not make use of this, as we are able to work directly with the semi-invariants of our group actions. Another important application, which we do not touch on here, is the construction of a compactification of the moduli space of curves as a projective variety.